Open source projects are great. You can download all the information, buy the components, order a custom PCB, assemble them, and boom, you have a working whatever. But that's not always the case. Since we usually learn more from mistakes and when there are problems rather than when everything goes smoothly, this video is all about the struggle, the stumbles, and the mistakes I made trying to get a supposedly very simple build that almost made me give up. This is a SID chip, the legendary sound chip of the Commodore 64. And this is also a faulty SID chip. Unfortunately, SID chips are very delicate and fail more often than a lot of other chips. That, combined with the fact that it's a custom chip that Commodore stopped manufacturing sometime in the 80s, and that the insides are quite complex, means that SID chips go for a pretty penny these days. I've actually been working on a video about modern replacements for SID chips. Yes, that video is still coming, even though I started preparing it almost 3 years ago. If all goes well, it should be out within a few weeks from now. I'll make sure to link it in the description when it's finally out. There, I'll also talk about what makes the SID chip so unique and how it's implemented internally. One of the many steps in making that video was building a nano SwinSID. That's one of the first open source SID replacement projects that were created. It's not supposed to be one of the best SID replacements out there, but I figured it would be a good baseline to compare other replacements against. In theory, it looked like a pretty straightforward build. Small PCBs, simple microcontroller, and only about 5 or 6 SMD components. I have built way more complicated projects than that without any problems, like the RetroChip Tester Pro or even the TMS RGB converter for the TI-99/4A, so this shouldn't have posed any particular problem. In theory, at least. I honestly wasn't even thinking about making a video about this, or maybe I would record a little bit of the process and then put it on the Noel's Spare Parts second channel. But things started not going right pretty quickly, so I decided to turn it into a full video and show how sometimes things don't go the way you expect them to. But let's not get ahead of ourselves and let's go back to the beginning. The Nano SwinSID project started all the way back in 2005. That's almost 20 years ago. Does that make it a retro piece replacement? It was started by Swinkles and multiple people contributed to it until its recent form. All the work is done in an Atmega 88 microcontroller with a tiny PCB in the form factor of a 28-pin through-hole chip that fits right into the SID socket. Very neat and simple. The schematic also shows that it's pretty trivial. It really is just a microcontroller, a crystal oscillator, and a few voltage dividers and decoupling capacitors. There isn't much more than that. For most of the build, I used the grid instructions in the To Layman page, I'll leave a link in the description, which includes everything you need to make this project. Unfortunately, I don't have a lot of footage from the beginning of the build since I really didn't think this was going to be anything special. So the first thing I did was order the PCBs from today's sponsor, PCBWay. As usual, the whole process was very easy. You can download the Gerbers directly from the project page and upload them to PCBWay. You really don't need to make any changes to the options after you upload it, but I changed a few things. I changed the amount to 10 because it's the same price to order 10 PCBs than 5, which is the default for such a tiny PCB. And I also changed the color to yellow because, I don't know, I have too many green PCBs. And a few days later, the PCBs arrived in the mail. The first thing I did was to assemble the components I was going to need for the build. Also, one tip is that when you cut a few components from the strip, they become quite difficult to tell what they are. So I like to label them and tape them on a piece of paper to make sure I don't get them mixed up. And with that, it's time to pull out the microscope and start doing some soldering. I'm starting with the microcontroller since it's the most difficult component and it's pretty flat. I really thought this was going to be pretty straightforward, but it gave me so much trouble. So I first cleaned the board with isopropyl alcohol and added lots of flux. Next, I tinned a couple corner pins to help me with initial soldering of the chip. It's very important to line up the pins of the microcontroller with the pads correctly, but even more important is to make sure you have the right orientation. See that big circle on the bottom right corner? That's indicating pin number 1. And especially on this board, the microcontroller is actually upside down with respect to all the markings and the other components, so watch out for that. And this is where things started going south. One mistake I made right away is that I'm using the thinnest tip for the soldering iron, and it's just not ideal for soldering a microcontroller like this. Maybe for tiny isolated components, but just not for doing lots of pins this way. See, Supposedly, I already soldered a corner, but the microcontroller isn't attached at all. If it's not sliding all over the place, it's because there's a metric ton of flux underneath. So I tried again and, okay, maybe it worked this time? So let's do another corner. Also, as you can see, the soldering job is not looking great. The solder is mostly bunching up on the pads and it's not really surrounding the pins very well. But I kept going and I figured I could make it better later. And yeah, the tip is really bad in here. The solder isn't even going on the pads, even with all the flux. So I think I'm just not transferring enough heat to the pad. So I added some more flux and tried drag soldering a whole side and whoa, the whole chip is moving. I didn't manage to solder a single pin correctly. Wow. I tried repositioning the chip and soldering it again. But just nothing. No matter what I did, it would not stick to the board. All right, let's do this again. This time I tinned all the pads to make the soldering easier. The chip is covered in flux, but whatever. As long as I clean it at the end, it's only going to help with soldering. This time I tried drag soldering from the beginning and it seems to be working. At least the chip seems attached this time, but there isn't that much solder, so I'm gonna make another pass and add some fresh solder. And okay, after cleaning the flux, it's not pretty, but at least it seems soldered in place, so that's something. The rest of the components were totally straightforward, but I struggled again making the connector for the programming port. The ATmega88 uses 6 pins for a programming port, but in this particular design it uses a 1.27mm pitch, which makes it a bit challenging. My initial thought was to solder some cables to a strip of 1.27mm pin headers. Very simple in theory, but the pin header strip is very small and flimsy. First of all, the pins were so close together that in order to solder the cables to them, I had to bend them to the sides. And then, in my first attempt at tinning the pins, apparently I put a little bit too much heat in the strip and it just collapsed by itself. So I had to be a little bit more careful soldering the cables, but with some patience, I got it to work in the end. Although it definitely feels a bit flimsy, it doesn't exactly inspire me with confidence. The next step is to program the microcontroller with the SwinSID Nano firmware, and that's where the next problem came up. I have this programmer that is supposed to work with ATmega microcontrollers. As a matter of fact, I've used it in the past to program the one in the Retro Chip Tester Pro, but that is an ATmega 2560, not an 88PA, so it's slightly different. The problem is that the cable from the programmer doesn't fit the connector on the SwinSID Nano, so I have to figure out which signal goes where. Not a problem, right? Well, on the SwinSID Nano side, things are very clear. It is very well documented on the webpage, so the signals are laid out in this particular order. Good. On the programmer, however, things aren't very clear. The pins aren't labeled anywhere on the programmer. All I see are numbers 1, 2, and 3, but nothing else, and those don't even look like pin numbers, they're more like rows. Fortunately, I was able to track down the user manual for the programmer in German, but the signal names are universal, and well, it's not helping too much. I see the labels on the 6-pin connector, but it's not telling me how they are oriented in the real programmer. I see there's a notch on the diagram, but there's no visible notch anywhere in the connector itself. So in order to solve this, I had to resort to plugging in the programmer and looking for VCC and ground with the multimeter. This is what I even had to reverse engineer the connections from the 2-row pin to the one, and it's actually pretty straightforward. It's just like 1, 2, 3, 4, 5, 6. So what I'm going to be using for this is the command line ARV dude. I'm not really sure why it's called that way. I always thought it was a funny name, but I've used that in the past and it's actually really straightforward command line utility. And before I do anything else, what I'm going to do is I'm just going to make sure that we're communicating correctly with the ATmega microcontroller. I tell it which microcontroller we're dealing with, and I tell it which programmer this is and which COM port to find it in, which I know Windows is correctly recognizing it, so the driver is fine. So let's see. And yeah, this is what I was afraid of. So we get all of this, which I'm not sure it's telling us too much. I think it's mostly just telling us the configuration that I just told it. Yeah, it's COM3 and it detects it in COM3. I know this warning is normal. There's something about this command line that it tries to send some command that is not interpreted correctly by most programmers. That's fine, but this is not okay. It should end with initialization correct and like, programmer waiting or something like that. And instead of that, yeah, initialization failed. What do we check now? Is it this connection that is not quite right? Do I need to be, let me see, let me hold it up a little bit. Sometimes you need to push it a little bit to make better connection. No, I made no difference. I know we're powering this, so I should check that we have the right voltages and everything. We are in 5 volts. Well, I think I just did something really stupid, and I'm leaving it here because we all make mistakes, and part of this is learning from each other. I know I'm gonna learn from this one. One of the first things I decided to do was to check that we are correctly powering the microcontroller through the connector. So I was checking VCC, and I don't know what I was thinking, but I was being really stupid. So I was having the ground lead in there, and I was trying to hit the VCC line on the microcontroller, and you know where this is headed. The VCC line on the microcontroller is right next to a ground pin, and those are tiny, and this is not, and my pulse is not perfect. And I went like this, and I must have shorted them, and I heard a little bzzz, and I even smelled the magic smoke being released from there. So, I don't know what I was thinking. Because it's connected just to the USB, I don't have a power supply. I know it's the same thing, but it probably wasn't ringing the alarm bells. But of course I am measuring voltages, it's being powered. And yes, you should never be measuring those tiny pins with this. So don't be an idiot like me and do that. So I think we can safely discard this. Once the magic smoke is released, that's it. This is one of the worst times when building a project. You got all the components, you assembled everything, you go and try to use it, and nothing happens. And in this case, it's not even that. It's just when I go to program it with a microcontroller, which for me at least has always been a tricky moment, then it doesn't work. But that's not the end of my frustrations with this project. The connections on the PCB for programming the microcontroller are really suspect. Are they really making correct contact? I hope so, but I'm not 100% sure. And even if that's okay, is the microcontroller working correctly? Did I solder it correctly? Is there a pin somewhere that is not making the right contact? Or heck, did I even overheat it too much while I was soldering it and I damaged it and now it's not working? There are just way too many unknowns and too many points of failure, which is making this very frustrating. Just building another board would be just as frustrating. So I'm going to do a few things to reduce unknowns. First of all, I'm going to build 2 new boards. That way, if things don't work out in one, they may work on the other one, and if not, it's very unlikely that I just got a pin soldered incorrectly in both. Next, I'm going to connect the programming cables in a different way. I really wasn't happy at all about building that connector, or even the way that it made connection with the PCB itself. So this time, I'm going to solder programming cables directly to the PCB, and I'll just remove them once I get everything working. It's not like I have to do that multiple times. And finally, I found a video of someone programming this exact same microcontroller for this exact project actually, which makes it great, with a different microcontroller device. Since it's not very expensive, I have just ordered it from Amazon and I'll use that one. So alright, here we go again. Back to soldering in the microscope. This time around, I decided to use my normal chisel soldering tip. You think it would be too large for this kind of fine soldering, but since we don't care if we touch multiple pins at once, it makes drag soldering and general heat transfer much better. And yeah, this time I was able to solder the microcontroller much faster. Sure, I put a little too much solder initially, but that's easy enough to remove with some weak and braid. Much better to have a little too extra solder than not enough, obviously, as long as you don't short anything. First thing I did is to make sure that I didn't have any shorts between pins, and then, to be extra sure, I used some tweezers to pull on every pin to make sure that they're correctly soldered. And good thing I did that. Check out this corner. It moves just a little bit. I wonder if that was happening in the previous board since I didn't really check it that thoroughly. Anyway, we can add a little bit more solder and I think that's good. All the other pins checked out fine, so let's try programming the microcontrollers again. And here's the programmer that just arrived from Amazon. This is called a USB ASP, and I see a lot of references to people online using it to program this exact same microcontroller. It actually needs some very specific drivers to work correctly on Windows, but you can actually install those with a custom program, which is called Zadig, that lets you install very specific drivers for your USB devices. As usual, I'll put a link in the description to that program. So this is what it looks like after I solder the cables. And let me tell you, this was a major pain to solder. The through holes in here for the connector for the programming, they are tiny. I was hoping that soldering the cables would be a lot easier. It was a pain to solder cables on the pins because they're so close together, so they have such a fine pitch. It was hard getting the cables through. Part of it is because they were not solid cables. They have multiple strands, so it made it really difficult to get them through the holes. And then it was very easy to solder one and then accidentally put a little bit of solder in the next hole. And yeah, I'm shocked that I got it working. I even checked it a few times with a multimeter to make sure that there were no shorts or anything, so that's fine. But that's not the end of my problems. So I go ahead, I'm like, okay, let's connect it. And one of the really nice things about this one is that it has this kind of breakout board and it has all the signals labeled. So that is a big step up from the other one. But see what I've done here? Yes, so I painfully soldered female cables, and I needed male cables to connect it here. So what I'm gonna have to do is use something like this. So I've put something like this together, several male to male cables, and I put them together so I can just put them like this right here. And now I need to figure out which one goes here. Yes, I didn't have the same color, so I'm just gonna have to go one by one, figuring out which one corresponds to what. But these are pretty solid connections. So I believe that once I make those connections, we should be good to go. So will it work? We'll find out in a couple minutes. Okay, that's encouraging. We have the power LED turning on, so that's great. So again, I'm gonna use the AVR dude, and this time I need to tell it that I'm using the USB SAP programmer. Okay, so it is detecting the programmer. So this one is a little different because it doesn't use a COM port like the other one, but it detects it just fine. But I believe this is initialization failed. So I think it's not able to talk to the microcontroller. It's time for plan B, and that's why I made another one of these. I figured chances are something would go wrong after the experience of the first one. So it's a good thing to have another one. Who knows? For all I know, one of those pins is not soldered correctly in the other one, and then this one will just work. But I'm going to do this one a little bit better based on what I learned in the other one. So first of all, I'm going to be using these cables to solder them into the programming connector. These are the kind of cables you use on a breadboard, and they have solid wire, so it makes it infinitely easier to put through there and solder them there. So that's the first upgrade. The second upgrade I'm going to do is the connector. So I'm going to use the right cable, because remember that eventually we want to connect to this connector. So eventually we need a male connectors that go there. So what I'm going to do is I'm going to, and I've already kind of prepared this, I'm going to use these cables. So the male connectors will go right here, like that. And these guys are going to go into just a set of pin headers, just like that. And then I will solder the cables to that, which should be very easy. And again, even protect them with a heat shrink. number 6 is ground, and so that's the black one here. Then that goes like that. Now that was pretty smooth. Okay, let's see what happens. Okay, good. At least we have the power light. This is the moment of truth. Same thing. USB ASB. Atmel 88p. Verbose. And we have the exact same thing. Things are just not looking good. I wish we would get past the initialization, but we're always getting stuck there with that error. I'm going to check that all the signals reach the microcontroller correctly. Hopefully I won't short it and blow it up like last time. I'm gonna get VCC here, and I know by looking at the datasheet that VCC should be pin 18 on the Atmega, which is right here. There you go. And yes, this is not powered right now. I'm not gonna make that same mistake again. So ground, for example, is on pin 4. Yep. No. This one is not reaching here. MISO is supposed to get all the way to pin 16. Interesting. It's this one that is not making good contact. Oh, look, it moves. Wow. What about those? It's fine. I can't believe I missed that one. Thought I had checked them all. I may give those a little bit of extra solder as well. That seems much better. Yeah. So not really surprisingly, the connectors here actually came loose while I was trying to test for continuity. I'm saying not surprisingly because these were the cables with, they weren't like solid core, they were just a lot of threaded filaments. And of course, just bending this a little bit, just, eventually they started breaking. So I spent a while just replacing them again with solid core cables, just like the other board that I was making, and I made the same kind of connector here. So now both of them will have the same connectors. So I checked all the other connections and they seem fine this time. There's continuity from every single one of the 6 connectors here to the Atmega chip, the best I could tell. So let's see if we can initialize it correctly this time. Oh, look at that. This time it managed to initialize it correctly. Wow. So it was just that corner pin that seemed to be soldered, but really wasn't. And actually, I was lucky because when I was testing continuity, I was pushing down on it. And sometimes that's enough to make it touch at that point. But then when you're not testing it that way with a probe, it's not making contact. So I was actually lucky. However, we're still not out of the woods. Something's happening here. Device signature doesn't match what it expects for the Atmega 88P. I wonder if it's because it's a PA. I don't know what the difference is between the PA and the P. And the device signature is very similar. It expects 1E9307 and you got 1E930F. But that's awesome. That is really good news. I mean, even if somehow the device signature doesn't come in through correctly, it even says it there, we can bypass that and attempt to program it and move on with the project. Wow, that's huge. Okay, well, now I'm going to go ahead and do the same thing with the other one. And maybe it's just another pin that is not soldered correctly. That would be awesome. So this is interesting. I'm checking the second board and I wasn't able to get a continuity between VCC and the VCC pins on the microcontroller. I know that 5 volts are getting to the board because we are getting the LED. So it's interesting that it's not getting there, and it's not even getting to the pad of the LED of the microcontroller, as far as I can tell. So I'll have to see what's in there. The other one is very likely a similar problem to what I had before, is with SCK, and that is one of the corner pins, this one in here, and it's not getting, but if I touch the pad, I'm getting it. So clearly that pin was not, again, soldered correctly, and I need to adjust that. But the VCC is a little odd. So again, let's look at it in the microscope. So SCK is the one in this corner over here, and apparently looks okay. There's definitely solder there, but is it? It looks fine. I can't move it. So that's surprising. So it could be the connector. It could be that the cable is not connected correctly, because this looks pretty good to me. And those were the, yeah, you can see VCC, those two in there. Those also look totally fine. And I tested the pads, and yeah, so I wonder if there's something going on with the connectors. Oh yeah, look at that. This is the VCC connector. Wow. Oh, it's so obvious under the microscope that it's totally not making the correct connection. I wonder if this is the sign so the top goes to one of the VCC connectors, the VCC pins on the microcontroller, and that's the one that was getting power and maybe the LED, and the bottom is the one that was getting to the two that weren't getting any. So definitely need to fix that one. Oh, that one also is moving a little bit. That's fine. Yeah, so those two need to be resoldered. You know, and while we're here, I know that pin wasn't wiggling, but I want to check if there is continuity. So first of all, yep, and this is tricky because it's so tiny, but I'm not getting any continuity. Wow, check that out. As soon as I touch it, actually, as soon as they touch each other, if I touch the pin, yeah, but not if I touch the pad. Look at that. So, wow, that's weird. I mean, even though it seems to be soldered correctly, it's not making continuity. I mean, that is just tricky. So I'm just going to reflow that and try that again. Wow. You know, things like that, it just, there's no way that visually, or even wiggling it with the tweezers like I was doing earlier, that you could have caught that. So it just makes you wonder how many other ones are that way. While I'm here, those look like they have very little solder. Are they wiggling at all? And those were the connection ones, the communication ones. And they seem to be fine. All right, I'm gonna leave him alone instead of making it worse. Let's see if we can initialize the microcontroller now. Okay, we got power, so good sign, and still nothing. So this one is still refusing to communicate. So I checked and all the connections are fine, all the way from the programmer, all the way to the pins of the microcontroller. So the next, maybe easiest thing to test is whether we're getting a correct clock signal from the crystal oscillator right here. And yeah, that looks totally fine. And yeah, look at that, 32 megahertz. So that's exactly right. I'm not going to reach in with this probe and try to see if he gets to the microcontroller, but I've already tested continuity between that and the correct pin when it wasn't plugged in. So it should be reaching that just fine. So that all seems fine. So I'm doing one last sanity check in here, and I'm just pulling on every pin as hard as I can, and they all seem fine. I was wondering about this one, and since that is SCK, I think, but then I ran into was it? That has some movement, and that is ground. Yeah, there's definitely a little bit of movement there. Now, is that enough? I don't know. So I'm gonna reflow all of them again, and maybe there's just too little solder, and I will do more like this side and make sure there's plenty of it. I'm not sure what makes this particular chip so difficult to get all the legs perfectly soldered. I've definitely done other chips of this kind with this kind of pitch and everything, I don't know, maybe I should have bent the pins down a little bit more. Maybe they're kind of lifted a little bit, and that's making it harder for the solder to make good contact all the time. I'm not sure. So I'm gonna go a little over the top now and make sure we have perfect connection there all the time. Okay, that looks much better, especially after I removed all the flux, and I think those pins are rock solid now. So if this doesn't work now, then the only thing I can think of is that somehow I've managed the microcontroller, in which case we'll go ahead and replace it with a new one. But let's give this a try. And still nothing. Okay, let's replace the microcontroller. I'm gonna try putting some Kapton tape in here before, just to avoid melting the cables, for example, or the crystal oscillator. Wow, there we go. It initialized the device properly, and it read probably, yeah, the device signature, and just like the other one. Wow, very, very cool. So I'm glad that with the new microcontroller, everything is working. And I was trying to think, why would the old one have failed? I mean, it could have been random things, or it could have been during the soldering, but I don't know. I have a feeling that those chips are pretty sturdy, pretty hardy. But I was thinking that is the board that had that loose VCC connector. So I wonder if just having the intermittent connection of VCC on and off like that was enough to cause some damage and make it so it would not communicate with the programmer. I actually just learned something very interesting, and I wonder if this affects some of the previous results. Hopefully not, but check this out. There are two USB ports in here. If I plug it in the first USB port, I do this, and it initializes and reads the device signature just fine. If I plug it in to the other USB port, we do the same thing, and it fails. So I'm guessing, and I haven't verified this is because the program that I use to use a specific driver for this device, it's tied to the USB port, and I probably used it when it was plugged in here. And if you plug it in a different port, it tries to use the default USB driver. So anyway, that's all done. So let's go ahead and try to program the firmware in the microcontroller. So all I have to do is AVR dude, same parameters as before, but we want to tell it that we want to flash that particular hex file. And so I think it's just complaining about that and it's not going any further. So let's try using that setting to force the device check. There we go. So it's going to write it, and then it's going to verify, it's going to read it back, and it's going to make sure that it's okay. Okay, perfect. To finish it off, we need to set the fuses to the correct settings. So from the project page, we see there are 3 fuses, and they're supposed to be, the lower one is supposed to be E0, height 1, DF, and the extended is F9. If all goes well, again, this should just go ahead and do it. Okay. Oh, there's a mismatch. In the high and the low are set correctly. The extended one is not. I wasn't sure if AVR dude was going to be able to set the extended one. Let's try that again. Yeah, so he fails with the extended one. Coincidentally, I just had my friend John stop by. He has a retro channel called BigBadBiologist, and you should definitely check it out if you're especially into vintage Macs and live repairs. He's really good at that. Anyway, he reminded me that this EEPROM programmer that I have, and he also has that one, the XGeku Pro T48, this one, or the more popular TI-866, I think it's called. Not only they do EEPROMs and a bunch of other chips, but they also do Atmega microcontrollers through this port. So you don't even need a special adapter to fit it in the ZIF socket. So it may be interesting to check this out and compare it to the AVR dude. So let's give that a try. So this is the same interface you may be used to from EEPROM programming. You just have to select the right microcontroller there. So there's like tons of chips when you select that, and you can just type the name, and that's one of the options. And it's nice that it's all the way to the A, so it definitely is prepared for that, unlike AVR dude. And then the other key thing you need to do is tell it to use the ICSP port. And that's the port in front where we connected the cables. Right, and it even tells you, go ahead and check out the wiring diagram, which is right here. So that is, at first I thought I needed some kind of adapter, but it has right here, built into the program, very, very convenient. There's the 6 cables that you need, and they go from there to those particular ports on the Atmega. So I went ahead and I did exactly that, and they're ready. So you can see there's those 4 in there. I don't know if you can see it. There's those 4 in there, and they're mapped to the correct connectors. Before we do anything else, let's do an ID check, and let's see if that works. So there you go. Red device. Okay, perfect. So let's go ahead and read the contents. I think we can do that, right? And hopefully that will tell us the fuses. Oh, there it is. It tells you here again, just in case you missed it, the wiring that you need to do. And there you go. So that looks to be the contents of it. The fuses are the way we set them up, but the extended fuse is FF. And I believe we want it to be F9. So I wonder if this program will let us set it correctly. So I think you need to go to config. Yeah, so they don't let you enter a value directly. There you go. So that would be F9. Program it, and we just want to program the config. Yeah. Okay, so it's giving us the same error as AVR dude. It's saying it's trying to set the extended fuse to F9 and is returning FF, so we're not able to set that. I don't know if that is a problem or not. I don't know what we're using those numbers exactly. But both boards do it, which is very suspicious. So I think at this point, I'm just going to go ahead and put the pin headers and test it and see if we have a working SID replacement. There's the commutator that I'm using for all the SID replacement tests. So that makes it very nice and convenient to just drop it in. And now I can just turn it on. And we get absolutely nothing. This is set up to play Cybernoid as soon as it turns on. I have a cartridge plugged in, a Kung Fu cartridge. But I also know that the SwinSID Nano is supposed to make a beep sound when it turns on, and we got nothing. Let me try it again. Nothing. How disappointing. Well, that's it. I have failed. Of course, at this point, I just have to start wondering, are those legit Atmega 88 PA controllers, or did they sell me counterfeit ones? It wouldn't be the first time that has happened, and I did buy those from some random seller on eBay a few years back, so suppose it's possible. But then I remember that these chips are cheap, dirt cheap. So surely there's no profit trying to restamp other chips to pass them as Atmega 88s, right? Well, you know me. I am nothing if I'm not stubborn. Yesterday, I placed an order for a few Atmega 88 PAs from a reputable source, Mouser, and I'll build another board with those. Will that fix it? I have no idea. The microcontrollers from Mouser just arrived, so before I do anything, let's compare them to the other ones I was using. These are the ones I've used in this project so far, and these are the ones from Mouser. They certainly look different, but that doesn't necessarily mean anything. I know a lot of chips get manufactured in different factories, sometimes in different countries, and sometimes the markings are quite different. However, the original chips I was using have a kind of weird font to them. They seem much bolder and also fuzzier. And the ratio of the Atmel logo is different between the two chips as well, so that's very suspicious. But there's only one way to find out. I'm going to take the very first board I built, the one I shorted out and killed the microcontroller, and I'm going to swap it out with one of these new ones. That way I don't have to rebuild everything. And you know what? Maybe it's just more practice. But this one felt a lot easier to solder than the other microcontrollers. What's going on in here? Here's the board with the new microcontroller, and I also soldered a similar connector so we can connect it to the programmer the same way as the other ones. That just makes it way easier to swap back and forth. And so let's go ahead and connect it to the, I'm going to use the EEPROM programmer just because I like the interface better, and let's see how that works. So first thing, I'm just going to try to do an ID check. All right, I told it to use the zip socket. No, I'm going to use ICSP port. Yep. ID check. So we read it correctly. Oh, wow. So now we report 1E93 like before, 0F, which is what is supposed to be for the ATmega88P. The other one was reporting 07. Wow. Okay, let's try to program it. I also set the correct fuses, both for the low, high, and extended. And so now everything went successful. Let's try reading it back. Yeah, so all the fuses are set correctly. Wow, did this do it? Let's try it on the Commodore with the updated microcontroller. And here's the moment of truth. Oh. Wow. So in the end, it was a batch of bad microcontrollers. I can't believe that. I couldn't just let it go at that. So I decided to dig a little deeper. And maybe I should have done this before, but I looked up the device ID that was reported in the initial microcontroller, 1E9307. Surprisingly, it's not that easy to find the device from the device ID, but I found this list compiled by my friend Rees from the channel Ctrl-Alt-Rees, and there we see that the ATmega88PA is 1E930F as we expected, and the 071 is an ATmega 8. What? The ATmega 8 is a very similar microcontroller to the 88A. Same amount of flash RAM, same form factor. Looking at the datasheet for the ATmega 8, I see right there the device ID. But this is what confirmed everything for me. The ATmega 8 only has 2 byte fuses, low and high. It has no extended fuse, which is why both programmers refused to set it and always read it back as uninitialized. So what I really bought originally were ATmega 8 microcontrollers rebatched as ATmega 88PA. And what makes this even crazier is that an ATmega 8 seems to be slightly more expensive than an ATmega 88PA. So all I can think of is that the process of rebatching and maybe even recovering chips must be really, really efficient and cheap to make it worth their while. So wow, I still almost can't believe that I got counterfeit $1 chips. So there you have it. In the end, I managed to get it to work. It really was touch and go for a while, and I was ready to throw in the towel more than once. In the end, I had a few very clear takeaways from this whole ordeal. The first one is that fine pitch connectors like the one used for programming the SwinSID Nano, they're just a pain. I'm surprised they were not able to find room for fully sized ones somewhere in that PCB. I think there's room. The second one is that soldering SMD chips like that one can be really challenging sometimes. I still don't know why it was so difficult, but next time I might look into the legs and make sure that they're bent enough to make the proper connection before I solder them. The third and last one is that programming microcontrollers can be a little scary until you find the right combination of cables and programmers that works. Then it's trivial. In the future, I think I'm going to start with the EEPROM programmer since I think that supports lots of different microcontrollers and the interface was great. So anyway, I hope you also learned something from all of this, and I'll see you in the next video.